Today, we're going to dive into a hidden world of physics that is quite literally all around us. It's in the air we breathe, the water we drink, it's even inside our own bodies. We are talking about fluids, and their secret properties are responsible for some truly mind-bending stuff. So let's kick things off with a couple of mysteries you've probably seen 100 times. Picture a water spider just gliding across the surface of a pond, like it's no big deal, totally defying gravity. But have you ever really stopped to think, how is that even possible? And then let's flip that on its head and think about the other extreme, a massive, multi-ton truck grinding to a halt. How can a simple push from a person's foot stop something so huge? Well, believe it or not, the answer to both of these puzzles is hidden in the physics of fluids. To really get our heads around this, we've got to start with the basics. What exactly is a fluid? We throw that word around all the time, but in the world of physics, its meaning is actually pretty specific and maybe a little surprising. Okay, so here's the fundamental difference between a solid and a fluid. It's all about how they react to being pushed around. A solid, it fights back. It tries to hold its shape. But a fluid? Nah, it just gives in. It flows. And that one simple characteristic is what makes them so incredibly unique. And when we say fluid, you might just think of water, but the category is huge. We're talking about the air we're breathing right now, the toothpaste you use every morning, even things like flour dough and the molten lava deep inside the earth. The rule is simple. If it can flow, it's a fluid. All right, now let's dig into a really fundamental property of fluids when they're just sitting still. There's this hidden force they're always exerting on everything they touch. We call this force pressure. And honestly, it is the key to understanding so much about our world. Now, here is the crucial thing you have to remember about pressure. It's not just about how hard you push, it's about how focused that push is. A gentle push with a really sharp point can create an insane amount of pressure, while a huge force spread out over a big area might feel like nothing at all. A sharp knife is the perfect example of this in action. You're not using some kind of superhuman strength, right? But because the blade's edge is so incredibly thin, you're concentrating all of your force onto this tiny, tiny area. And that creates massive pressure, enough to slice right through things. It's a simple but brilliant piece of physics. So this whole idea gets even more interesting when you start going deeper into a fluid. Just imagine you're in a swimming pool. The deeper you swim, the more water is literally piled on top of you, and all that weight is pushing down. That's increasing the pressure. And this relationship can be described with this surprisingly simple formula. And you know what's really wild about this? The pressure only depends on the depth and the fluid's density. That's it. So the pressure 10 feet down in a massive lake is the exact same as the pressure 10 feet down in a skinny little pipe. The shape of the container just doesn't matter at all. To really let that sink in, think about a swimmer who's just 6 meters underwater. That's not even that deep. The pressure from the water above them is immense. It's about 60% of the Earth's entire atmospheric pressure. All of that force from just a few meters of water. So we've seen how pressure works, but now let's talk about how we can use it to our advantage. This is where things get really, really cool. And it all comes down to a principle known as Pascal's law. This right here is a total game changer. Imagine you've got a sealed container full of water. If you push on it in one spot, that pressure is instantly and equally felt everywhere inside that container. It's a simple idea, but it is the secret behind some of our most powerful technologies. A hydraulic lift is the perfect way to see Pascal's law in action. You push with a small force on a small piston, and that creates pressure in the fluid. That pressure travels through the whole system and pushes up on a much, much larger piston. And because pressure is force per area, that same pressure acting on a larger area creates a much, much bigger force. And the math behind it is just beautifully simple. The force you get out is just the force you put in, multiplied by the ratio of the areas. So if your second piston has an area that's 10 times larger than the first one, boom, you get 10 times the force. It's like having superhuman strength, all thanks to some clever fluid dynamics. And this brings us right back to that truck mystery from the beginning. When you hit the brakes in your car, you're using Pascal's law to take that light tap from your foot and multiply it into enough force to stop a massive moving vehicle. It's just an amazing piece of everyday engineering. Okay, so we've seen the incredible, raw power of fluids under pressure.
But now we're going to shift gears completely and look at a much more delicate, subtle force, one that works on the very surface of a fluid. All right, time to go back to our little water spider. How does it do it? Well, the secret isn't pressure from below. Nope. It's all about the tiny, invisible forces at play between the water molecules themselves.
Now, to really get this, we need to know about two types of molecular forces. First, there's cohesion. That's the force of attraction between molecules of the same stuff, like water molecules sticking to other water molecules. Then there's adhesion, which is the force of attraction between molecules of different substances, like water sticking to a glass.
So imagine a single water molecule deep down in a glass of water. It's being pulled on equally in all directions by all its neighbors, so the net force on it is zero. It's perfectly balanced. But a molecule at the surface, well, it has no molecules above it, so there's this unbalanced net inward pull coming from all the molecules below it, tugging it back into the liquid. And when every molecule on the surface is being pulled back into the liquid like that, it creates a kind of tension. The entire surface is forced to contract and tighten up, trying to get to the smallest possible area it can. It basically starts to act like a stretched elastic membrane, like the skin of a balloon. And that tension, that stretchy skin effect on the water's surface, is what we call surface tension. It's this force that's strong enough to support the weight of that water spider, letting it walk across the water as if it were solid ground. And there you have it, mystery solved.
So, let's do a quick recap. We've seen how pressure is all about force over area, and how it gets stronger the deeper you go. We've learned about Pascal's law, which lets us transmit pressure and multiply force, like a superpower. And we've uncovered surface tension, that elastic-like skin on liquids created by molecules pulling on each other. Pretty amazing stuff.
From the colossal power that lifts a car to the delicate balance that lets an insect skate on a pond, the hidden physics of fluids is constantly at play. It really makes you wonder, doesn't it? What other invisible forces are out there, quietly shaping our reality in ways we don't even notice?